Okay, so now we're at the point where we can actually try to show the first part, which is that circuit set is NP complete. And there's theorem. Okay, so we're going to try to show that circuit set is NP complete. I rewrote in blue here, I guess, what the definition of circuit set is, just to remind you. To show that something's NP complete, as you know, we need to do two things. We need to show that it's in NP and then give reduction from every language in NP to that circuit, to that language, I should say. And so our first part, we need to show that, in the first part, we need to show that circuit set is in NP. And this is not too hard. In fact, we can use that alternate definition of NP that we discussed. We can express circuit set as this, which is this language, in the following way. We can express it as those circuits C, where C is a Boolean circuit, for which there exists an X such that the pair CX is in R, where R is the language which takes a pair, which is a circuit and a string, and just accepts if that circuit on that, I don't know why that keeps happening, that circuit on that string evaluates to 1. Okay, and I think you can see that that is another way of just stating the language circuit set, and it fits the format that we said was an alternate way of defining NP. There's the witness. The witness is the string X or the assignment, and it can be checked in polynomial time because you can check, given a circuit and an assignment, whether that circuit on that assignment evaluates 1. Okay, so it's in NP, and let's now proceed with the reduction. So again, there's the definition of the problem of the language. And now we need to do this reduction. So for each language in NP, we need to give a polynomial time reduction from that language to circuit set. So, you know, this is a generic reduction in the sense that we're taking an arbitrary language in NP and carrying out this reduction. And, you know, one of the things that kind of guides you when you have a generic reduction like that is that you don't really know much of anything. So what do we know about A? Not much, except that it is a language in NP. So it means that it can be expressed in the following form. It can be expressed as the set of X, such that there exists a Y, such that X, Y is in R, where R is some polynomial time language, meaning that there is a Turing machine M sub R that decides this language R in some polynomial time bound, and let's give it a name, n to the C, and we'll call it G of n, n to the C for some constant C. Okay, so that's our generic NP language, and we're now going to try to reduce that to circuit set. And to do that, we're going to use something called the Turing machine tableau. Now, I'm not sure if in an earlier lecture you would have covered this, so I'll just tell you what it is here. I hope that you do know, however, what a configuration of a Turing machine is. So configuration is sort of instantaneous description of the Turing machine. It has the contents of the tape and the position of the head and the state. And if you organize those configurations of a Turing machine M sub R on a given input as it runs, you organize those configurations one after the other, one on top of the other. That's called a tableau, and then you kind of pad them out so you make a nice array. So in this example, where the input, where the machine that we're thinking about is M sub R, that's the verifier for the NP language A that we're talking about. So that's our polynomial time Turing machine. It has its input W, which in fact comes in two parts. It's the X and the Y. Just go back. Maybe just go back to remind you that there's the two parts of the input, which are the X, which is the instance of A, and then Y, which is the purported witness. So that is the input, and you know, in the tableau, we start out with the contents of the tape being the input, W1 through Wn, if it has n characters, and we're in the start state of the Turing machine, which is what this Q sub S means. Oh gosh, why does that keep happening? In the start state of the Turing machine, and that's the entire contents of the tape, and we just pad it out with blanks as far as we need. And then maybe in the next step of the Turing machine, maybe it you know, moves to state Q1 and moves its head over here. So this is the way I'm indicating the position of the head. I'm putting a slash and then the state, and so you can see, you can kind of follow where the head moves and what the state is as it processes things. And maybe in the next step of the Turing machine, you know, you move the head back to the first square, you stay in state Q1, and you write over the symbol here with an A, and so on, and you just keep moving along like that. Okay, so it's just a sequence of configurations of the Turing machine, one after the other, on top of each other. When you think of it, then the height of this tableau, meaning the number of rows in it, is just the number of steps that it takes before this Turing machine finishes, right? So it's the time, the running time of this Turing machine, which is in this case, the length of the input, length of W raised to the C, which was that constant. And the width is, well, no larger than the amount of time. It's the space usage. It's the number of squares that you end up touching as you execute the Turing machine. And of course, in time W to the C, you can touch no more than W to the C cells. Okay, and then there's one tiny little detail that will be important for our proof, which is that we can always standardize our Turing machine so that it moves its head to its leftmost square before accepting, so that if the Turing machine were to accept, we would see in this leftmost square the state Q sub A, which is maybe the accepting state of the Turing machine. Okay, so the important observation, like the key observation for this proof, and actually just a very important observation about the functions of Turing machines, is that the computation is local. In the context of a tableau, it means that the contents of a cell in the tableau is determined by the 3 cells above it in the tableau and no others. So you only need to look at the contents of the 3 cells above a given square in the tableau to determine its contents. And I drew some examples here just to sort of illustrate things. So for example, here's the cell we're interested in. And if in this time step, it has, maybe it has state, the head moves into this position, perhaps. Well, we know that from looking at the 3 squares above. We can see that the head, if it was going to move into this cell, it had to be either at most 1 to the left or 1 to the right. So we would see it among these top 3, these cells 3 above, the 3 cells above it. And we would see that the head is in this cell, and that's the contents of the cell, and the state is such and such, Q1 in this case, and therefore we know what the Turing machine will do in the next step. And so maybe we know that it moves its head here. If the cell in question has no head in it, then we would observe that from having seen, for example, that the cell above it has is in a certain state, reading a certain symbol, and so we know what happens. And in this case, the head moves off of that middle cell, and therefore, and we write over that cell with an A. Those are all things you can determine from looking at the contents of this cell in the tableau, right? And if the head is nowhere to be seen among the 3 cells above the cell in question, well, then that cell has to just stay the same. There's not a head that can move onto it. There's not a head in sight that can cause it to change or be overridden. Okay, so I hope that makes sense. If you look at the 3 cells above yourself in the tableau, you can determine what the contents of the contents of this cell. Very important. Okay, so now using that idea, we can do the following thing. We can build a Boolean circuit, which I'll call step, which takes the contents of 3 cells in the tableau and produces the content of the cell in that middle position in the next row. Okay, so it takes, and when I say it takes this is a Boolean circuit, so it takes bits and it outputs bits. So what I really mean is that you've decided upon a way of encoding in binary the contents of a cell in the tableau. It just has to have a character of the alphabet and possibly adjoined to it, concatenated with it, a character, a symbol which represents the state of the machine if the head is there. So it takes a few bits to describe that, and then it'll take a few bits to describe the cell here. So that's what the step function does. It takes those 3 cells and produces the cell below it. Okay, and again, what I should be careful to say, because we sort of defined a Boolean circuit, and we said, well, that there was a single output bit. So what I mean by this picture and by this assertion is that each output bit in this that's pictured here is some function of the input bits. And you just build a circuit, one for each of them, and put them side by side, and that's the step function that I'm describing. And the key thing is that because this step function looks at only 3 cells, and the contents of each cell is just a symbol from a finite size alphabet, the alphabet of the Turing machine, together with one of the states, and there's a finite number of states. The size of this step function, the size of the step circuit, is independent of the size of the tableau. The tableau may be enormous. The step circuit has a fixed size that depends only on the Turing machine. Okay. So now that we have a little circuit that produces the element of the square of the tableau in the next row, we can just put them side by side to compute an entire next row of the tableau from the row previous. So if we just put, if you remember that the tableau we're thinking about, which is the machine M sub r on input W, it had width at most the size of W to the C. So if we put a whole bunch of copies of the step function next to each other, then we can compute the entirety of a row of the tableau from the previous row. And in the interest of making the picture a little bit cleaner, I didn't draw all the connections here, but I think you can probably see this step function here has inputs which come from this cell, and this cell. This step function has inputs that come from this cell, this cell, this cell, and so on. And you have to do a little extra work to just do something at the end of the line here, because this depends only on the two above it. Okay, so now you've got a way of producing a Boolean circuit that computes one row of the tableau from the next one, the next row of the tableau from the previous one, I should say. And now, if you put together those, if you wire together a bunch of those rows of step functions, you can get a big Boolean circuit that computes from the first row of the tableau, the final row of the tableau, right? You just apply these Boolean circuits again and again and again. And then you can do a little bit of work at the beginning and the end to make something useful out of this. You can take some inputs which represent the symbols W1 through Wn, which is the input to this Turing machine. And again, they have to be encoded in binary to make them into a Boolean function. And you can just, there's a little extra wiring that you have to do here to insert this start state of the Turing machine and the head being on the leftmost square. Otherwise, just copy these things down. So that's a little pre-processing you do with a little bit of extra circuit nodes. And then at the end here, you can build a little circuit that just checks whether the contents of this leftmost cell at the very end of the computation contains the state Q accept, meaning that the machine would have accepted that input. Okay, and so that's another little tiny circuit that you add on. So with that little pre-processing and post-processing, you've ended up with a big Boolean circuit which outputs 1 if and only if that machine on that input would have accepted its input. Okay, and then so this circuit sort of awkwardly on the slide is called C sub M sub r comma W, because it's the circuit associated with that Turing machine M sub r on the input W. It has inputs W1 through Wn, and it has the feature that that circuit on input on the string W outputs 1 if and only if M sub r accepts its input, accepts the input W. And its size, I put in red here, is, well, polynomial in the length of W. And why is that? Because I think you remember we talked about the tableau having size width W to the C and height W to the C for that Turing machine, which runs in time W to the C. And the circuit that we built is just, it has like a little finite size component for each cell in this tableau. So its size is order, the size of the tableau. Okay, and actually, I mean, so this is useful for this reduction, but it's also an important statement, which is that we've proved that a Turing machine, the functioning of a Turing machine can be replicated by a circuit, a Boolean circuit, whose size is only the square of the size of the square of the running time of that Turing machine. Okay, which is another important statement, but for our purposes, we're going to use it in just a minute to finish this reduction that circuit set is NP complete. Okay, so let's remember that we're reducing what we're trying to do with all this. We were reducing from a generic NP language, which had the following form, to circuit set. And the reduction, which I'm calling F, which receives an instance of A, a string X, is supposed to produce the following circuit it is that circuit in blue here, which we've been talking about. It's the circuit C sub M sub R. It's the circuit which simulates the functioning of the Turing machine, which decides R, on input W, which you may remember has two parts, X and Y. And I've written them out here, X1 through Xn, Y1 through Ym. And this circuit outputs 1 if and only if XY is in R. And our reduction does the following little trick with this circuit. It hardwires the input X to be that X that we're reducing from, and it leaves the Y's as variables that are free. So it hardwires the X and leaves the Y's free. And if you think about it, that does what we want, because now you have a circuit where it's got a bunch of variables, they're just the Y variables, and there exists a setting to the Y variables that causes that circuit to output 1. If and only if, well, there exists a Y such that XY is a member of R, meaning, which is equivalent to X being in the language A. So this circuit, once we've hardwired X, has a satisfying truth assignment if and only if X was in the language A, which is exactly what a reduction is supposed to do. So I think, so that's maybe the picture to look at, and then we'll just sort of say it in words on the next slide. We have to check, at least the way I like to talk about doing reductions, kind of go through this 3 questions. Is the reduction polynomial time computable? Does yes map to yes, and does no map to no? So I'll sort of talk through those, but we sort of saw it on the previous slide. So is the reduction that we've described polynomial time computable? And I claim yes. You have to hard code the description of the Turing machine M sub R, it's a finite description. The K, which is the length of the witness Y as a function of the length of X, the Y is of the size of X to the K. And C, which is another number which describes the running time of the Turing machine, so some constant. And then the circuit, as you remember, if you remember, has the size of W to the 2C at most. And W has length, which is the length of X and Y together. X has length N, Y has length N to the K. And we need to really argue that you can write down this circuit and compute it, what you're supposed to write down as from the string X in polynomial time. And you can do that because the circuit has polynomial size, and I think you can sort of see from our description of it, it's just you stamp out the same fixed little step circuit just in basically a big grid and hook it up in a predictable way, except for that little bit at the very end and the beginning. So without going into too much gory detail, you can produce that circuit in time polynomial in the length of X. So it's polynomial time reduction. Okay, and then does yes map to yes? So that means, so if we have a string which is in the language A, well, then we know that there does exist a Y by the characterization that such that M sub R accepts XY. And well, that means that the reduction that we produce, that circuit that we produce, is a member of circuit set, because that means there exists a setting to the variables of the circuit, Y, that cause it to output 1. Does no map to no? Well, if X is not a member of A, then for all Y, M sub R rejects, which means that there is no satisfying assignment to the circuit that we've produced. There's no way to set the variables that correspond to Y in such a way that the circuit will output 1. So that's a reduction. Okay, so that's the first part. So that was a reduction that showed that circuit sat is NP complete.